All right, let's get right into it. We need to talk about the one thing that can absolutely bankrupt an AI startup. And no, it's not the cost of running models, it's the cost of training them. DeepSeek just dropped a paper on a totally new architecture that might solve one of the most expensive, soul-crushing problems in AI. This is the real alpha.
We've all been there, right? You've got the budget, you've rented that massive cluster of GPUs, and your model is learning. It's beautiful. And then, out of nowhere, the loss curve just shoots straight up to the moon. Your gradient explodes. You didn't just lose 2 days of work, you literally just set a pile of cash on fire.
And this isn't some rare freak accident. It's a fundamental risk you take every single time you scale up an AI model. They call it training instability, and it is the silent killer for any team that's trying to innovate without a bottomless bank account. So the real question is, how do we stop gambling with our fine-tuning budget?
Okay, let's break down exactly why this happens. I like to call it the $50,000 training trap, and it all starts with a very simple choice you have to make when you're designing your model.
So, you want to make your models smarter. You basically have two levers you can pull. You can go deeper, which means you stack on more and more layers, or you can go wider, meaning you pack more neurons into each of those layers. Now, going deeper is something we understand pretty well, but going wider, that's where the trap is. See, the problem is, the wider you make your model, the signal flowing through it gets exponentially more complicated. It's kind of like that game of telephone, you know? The more people in the chain, the more messed up the message gets at the end. In a neural net, that distortion turns into pure noise, which leads to these exploding gradients. The basic wiring we've been using for years just can't handle that kind of signal chaos.
And that chaos has a direct impact on your wallet. To stop your wide model from just collapsing in on itself, you have to do the one thing you don't want to do. You slow it down. You crank down the learning rate to play it safe. And what's the result? Well, your training run might now take twice as long, which means you just doubled your cloud bill.
So why are our models so fragile in the first place? Well, it turns out we've been building these futuristic AI skyscrapers using foundational bricks that were invented a decade ago. This isn't some new bug, it's a fundamental flaw in the original blueprint.
Just look at this timeline. Ever since ResNet gave us the skip connection way back in 2015, pretty much everything we've built has been a variation on that theme. Sure, we got things like hyper-connections in 2024, but those were just better versions of the same old Lego brick. What DeepSeek just did with mHC, this isn't a better brick. This is a whole new kind of brick.
Let's quickly talk about those hyper-connections, or HC. The idea was brilliant, right? Instead of a dumb wire, what if the connection itself could learn how to best mix information? Super powerful. But that power came with a huge catch. It was completely unconstrained. There were no safety rails.
And this chart from the paper shows you exactly what happens with no safety rails. It's measuring the signal gain. A perfectly stable connection should have a gain of 1. One goes in, one comes out. HSIC has a gain of almost 3,000. That is not a signal anymore. That is a feedback loop, a complete nuclear meltdown inside your network. And that's when your loss goes to infinity.
So how in the world do you tame an explosion like that? Well, DeepSeek's solution is it's elegant. It's all based in math, but the easiest way to understand it is with a really simple metaphor. I want you to picture the data flowing through a really wide neural network as a wild, open fire hose. It's got immense power, but it's just spraying chaotically in every direction. That chaos, that's your training instability.
So what mHC does is it walks up and puts a precision nozzle on the end of that fire hose. It takes all that chaotic force and constrains it, focusing it into a perfect, stable, powerful stream. It's the same amount of power, but now it's controlled.
So here's the magic behind the nozzle. mHC stands for Manifold-Constrained Hyper-Connections. It works by projecting the connections onto a special mathematical surface. This forces them to have a property called doubly stochastic, which is just a very rigorous mathematical way of saying they are guaranteed to not amplify the signal. They cannot explode. It's a mathematical certainty.
A mathematical guarantee is great, for the academics. But for the rest of us, does it actually work? Does it make the model better? Let's get to the results.
This chart is pretty telling. On the left, you've got the unstable HC model. Yeah, it improves, but it's a rocky road. Now, look at mHC on the right. The training is just this smooth, clean, stable drop. And here's the kicker. It actually ends up at a lower final loss. So it's not just safer, it's actually learning more efficiently.
And that more efficient learning translates directly into better performance. Just like at these benchmarks for a 27 billion parameter model, mHC is consistently outperforming the others. And pay attention to the really hard reasoning tasks, a jump of over 2% on both BBH and drop. That stability is paying off in the form of actual intelligence.
And this right here, this is the most important takeaway. This is basically free intelligence. You're not adding more parameters, you're not burning more GPU hours, you're just changing the topology, the shape of the wires inside the network. You get a smarter, better model for the exact same cost.
So what does this actually mean for you, for me, for anyone building with AI? It means the old rules might not apply anymore. This breakthrough suggests a whole new set of best practices.
So here's the playbook. If you're fine-tuning models on your own proprietary data, this architecture is an absolute game changer. By building mHC into your adapter layers, you can train faster, more cheaply, and with way less risk of a catastrophic failure. It's how you get the most out of your data and your compute budget.
And here's a prediction for you. You're about to see this pop up everywhere. The math behind mHC is just a perfect fit for things like LoRa and other fine-tuning adapters. I'd expect to see the major libraries start integrating this within the next couple of months. It just makes too much sense not to.
So the verdict is pretty clear. The AI arms race isn't just about who has the most GPUs anymore. DeepSeek is proving that real, fundamental innovation in mathematics can give you an edge that is more powerful and way more capital efficient than just throwing more hardware at the problem.
And that really leaves us with one final question to think about. As we're all racing to build these bigger, more powerful models, are we building them on a solid mathematical foundation? Or is the whole system we're relying on just one wide layer away from a total collapse? Something to think about.